Physics part 69. Physics part 69. A graph of load y-axis against extension. X-axis enables strain energy to be found even when the graph is not linear. We have shown the strain energy is given by strain energy W, which is equal to half F delta L is equal to half Fx is equal to half Kx square. The expression of half Fx represents the area between the straight line on the figure and the x-axis. This means that the strain energy is represented by the area under the line on a graph load y-axis plotted against extension of x-axis. A spring has an elastic constant of, I've got an example for you. A spring has got an elastic constant of 65 Newton meter and is extended elastically by 1.2 centimeter. Calculate the strain energy stored in the spring. Strain energy work is equal to half Kx square is equal to half into 65 into 1.2 into 10 power raised to minus 2 whole square, 4.7 into 10 power raised to minus 3 joules. Now it's your turn. Number one, a wire has an elastic constant of 5.5 into 10 power raised to 4 Newton per meter. It is extended elastically about 1.4 millimeter. Calculate the strain energy stored in the wire. 2. A rubber band has an elastic constant of 180 Newton per meter. The work done in extending the band is 0.16 joule. Calculate the extension of the band. The Young modules. The difficulty with using the elastic constant is that the constant is different for each specimen of a material having a different shape. It would be far more convenient if we had constant for a particular material, which would enable us to find extensions knowing the constant and the dimensions of the specimen. This is possible using the Young modulus. We have already mentioned the term strain. When an object of original length L is extended by an amount of delta L, the strain C is defined as strain is equal to extension over original length and delta E is equal to delta L over L. And strain is the ratio of the two lengths, does not have a unit. The strain produced within an object is caused a stress. In our case, we are dealing with the changes in length, so the stress is referred to a tensile stress. When a tensile force Fx normally to an area, the stress A is given. Stress is equal to force over area normal to the force, and A minus F over A. The unit of tensile stress is newtons per meter squared, Newton per meter. This unit is also the unit of pressure, and so an alternative unit of the stress is Pascal, PA. Well, we've got stress-strain graph, Young modulus for different materials. We've got a figure. We plotted graph of the load against extension. Since load is related to stress and extension is related to strain, a graph of stress plotted against strain would have the same basic shape as shown in the figure, 4.18. Once again, there is a straight line region between the origin and the L and the elastic limit. In this region, the changes of the strain with stress are elastic. In the region where the changes are elastic, it can be seen that stress to strain or removing the proportionality sign. Stress E strain, E into strain. Stress is equal to E into strain.